met this particular topic when we were talking about reaction of alkenes with strong acids. You can go back in your notes and check where we first saw this, but it's okay if you don't, because we didn't study it then at great length, and we will study it now a little bit more that we've seen it. There's actually a nice section in your text I just found. 6.2D. 6.2D. And it's literally starting on page 192 to 195. So what we're going to do now is discuss carbocation rearrangements, but for any reason, if anything's really peculiar or unclear, by all means, you can just look at these few pages right away and get to a better understanding of these things. But I'm going to walk through us really slowly. I prepared some special things this morning, new problems this semester to work on. So we'll simultaneously be practicing SN1 reactions, and at the same time, we're going to be learning a little bit more about carbocations, their nature, as well as rearrangements. Let's start with a SN1 reaction, a reaction that we should be able to identify as being likely to proceed by SN1 reaction mechanism. I'll just draw the water in both locations. Obviously, it's solvent. There's a ton of it, but just to remind you, there's lots of it. There's everywhere. I want you to consider it as the nucleophile as well. I want you to just draw the predicted product based on what we were just doing moments ago. No mechanism, just go right to the product. What is it? What's its structure? Some of you are going to think this is too simple. Just do it. Some of you are still learning this and are struggling a little bit more, but you should be able to write the product of this quite quickly. Okay. And the product we should have here would be an alcohol, right? That's what water does in these types of reactions. But something unexpected happens in this reaction when it's run. Two products actually form. And our goal, if we ever see a rearrangement to take place like this, the way that I test students about this is to explain using a mechanism the formation of these two products. So it'd be a situation where I might draw this whole thing out and say, give a detailed reaction mechanism that explains the formation of these two products. That's one way you can practice it or think about it. And a mechanism will help us explain this process. So we know right away it's an SN1 mechanism, so no need to do anything fancy. When the time is right, we'll know where we should be looking to explain this. First glance, direct substitution at this particular carbocation, easy to understand. If we look at the product here, you might think I'm made some horrible mistake or typo. We're going a little bit aloof today. But we have the same number of carbons. There's 6 carbons here, 6 carbons here. But the alcohol is attached to a carbon with 2 methyl groups. And the substrate has no carbon attached to just 2 methyl groups. We have 1 carbon attached to 3 methyl groups, 1 carbon attached to 1 methyl group. So clearly we can identify or look in this that there's been a carbon skeletal rearrangement. We can clearly acknowledge, maybe not explain why, but we can clearly acknowledge that things have been rearranged. All right, so let's cut to the chase here. And we have a secondary carbocation. Let's do the easy work first. Let's just explain the obvious product to all of us in the room. Just take water. Leaving group leaves. Nucleophile attacks. We get an oxonium ion by this process where we push 2 electrons here. And to get to this particular product, we just have to do an acid-base reaction where we subtract one of these acidic protons. Okay? And don't need to draw this. I'm not going to be grading on this particular point on our exams. We do have to get to this final product, but the key points will be, let's emphasize these. Leaving group leaving, nucleophile coming in. So here's where we should focus our attention whenever there's a rearrangement, at this carbocation, and then look at this particular product. This is a secondary carbocation, and this here is a secondary product. This we could say is a secondary alcohol. If this was chlorine, we'd say it's a secondary alkyl chloride. But this is secondary alcohol. The alcohol is attached to a carbon. That's secondary. This carbocation is secondary. It makes perfect sense. Here, if we look carefully, this is a tertiary alcohol. And we did see a little bit of this about 2 weeks ago on purpose. I kind of planted this little seed, and now we're going to see where it's grown in that time, and we're going to do something more with it. So when we have to explain a carbon skeleton rearrangement, it'll be the result of a carbocation rearrangement. And the way that we explain it is we will redraw this carbocation. So we're going to redraw this. First time we drew it was to explain the formation of a product that's easy for us to digest. Second time we draw it will be to figure out how we get to a rearranged or some sort of explanation that allows us to justify putting an alcohol in a strange place. The process that we use to do this is we redraw and re-evaluate this carbocation. And to do this systematically so that we don't make any possible mistakes, we're going to label this carbon right here alpha. It's just the Greek first letter in the Greek alphabet. Okay? It's arbitrary. We could call it A or 1. We just need to keep track of a few things here when we do this process. And the next carbons, as we move out from this has 2 carbons attached to alpha. We call these beta carbons. We're going to use this language next week, so it's good to introduce it now. So these are beta groups. And in this molecule, are these beta groups the same or are they different? Is this carbon the same as this carbon or different than this one? Well, we see that they're different, right? Thank you. And we're just going to arbitrarily call them beta 1 and beta 2. We could have called this beta 1 and this beta 2. We could have called this beta blue and this beta pink. We just have to name them something arbitrarily, and let's just look at them one at a time. Okay? So what we're going to do now is we will explore or examine beta 1. So to do so, let's actually redraw this molecule. And here's a carbocation, here's the alpha position, and here's beta 1. What I want us to do is I want us to expand at the beta 1 position. What I mean by that is I want us to just draw it in an expanded molecular formula. So examine beta 1, we just redraw it, and we'll do it by drawing an expanded molecular formula at beta 1. Okay, so all I've done is taken this, I want to expand this, I want to be able to see all of these bonds. There's 2 positions, so we're going to explore both of them. But today we're going to do beta 1 first. Now, the carbocation wants electrons desperately, and if it can get electrons from within the same molecule and make something more stable, it will. That's the basis for why these processes happen. We know that we're going to get to some sort of tertiary carbocation. We'll see it later. It's hidden off screen right now, but it's in your notes. But we want to examine, can we make something better right now? If we can, it happens spontaneously. So the way we do this is we use either hydride groups or alkyl groups. This group right here, hydrogen plus 2 electrons, is referred to as hydride. This is going to be called hydride, and this particular compound here is called sodium hydride. This would be called sodium hydride, but this group with 2 electrons is called hydride. Hydrogen with no electrons is called a proton. Hydrogen with one electron, well, it could be called a hydrogen, or it could be called a hydrogen radical. But the point is here that we have hydrogen with 2 electrons. We're moving or thinking about doing something with it. We don't call it proton. It's just that guy. Or that's just this little thing right here. Or this thing that's minus a proton. When there's 2 electrons, we call it hydride. It's usually negatively charged. This compound's called sodium hydride. You'll see it next semester. All right, anyway, 2 electrons, no electrons. We take these 2 electrons and move them here. So, first we redraw our carbocation. We find out all its unique beta positions. We start looking or examining one of them. At this beta 1 position, we have 3 identical hydrides attached. So we're just going to move a hydride. We're going to do what's called a hydride shift. So this is kind of like a little bit of just vocabulary here. But how do I want to draw this in our notes? How about we redraw this? I'm just going to get a fresh piece of paper and redraw this. Maybe you don't want to, but I'm going to do it. If you have room in your notes, you can just draw directly on this. But we're examining at the beta 1 position. I've expanded at the beta 1 position. This is alpha. Beta 1. We have 3 identical hydrides here. I'm just going to circle this whole puppy here. I'm going to move these electrons there. And what this is called is a 1,2 hydride shift. We're literally taking these electrons. That's what this arrow means. We're going to move them here. What do we get if we do that? There's this new species look like. There's already 1 hydrogen in this position. I haven't drawn it in here. You can go all the way back to where we started with iodine. There's 1 hydrogen already here. But if we move this hydride from the beta 1 position to alpha, what type of carbocation do we make here? This is primary. In this particular process, we went from secondary to primary. We went from more stable to less stable. This particular process is impossible. We'll reject this. But we're going to explore these things systematically, and you should as students, so you don't miss anything. So the beta 1 position made something less stable, and if we look at this carbocation here, if we look at this carbocation we just made, if we were to add water here, it wouldn't give us this particular product. And we were belaboring this point that this is a tertiary alcohol, so it should come from a tertiary carbocation, and here we made a primary carbocation. So this doesn't get us in the right direction. Energetically, it goes an unfavorable way. We'll always know we can reject this. So no need to panic. This is a practice exercise. I'm going very slowly through it. Let's expand or explore at the beta 2 position. At the beta 2 position now, we have alpha. This is our beta 2 position. And we have 3 methyl groups here. Okay? So we're just going to redraw this now. And what I've done here is I've expanded or written expanded molecular formulas at this beta 2 position. And what's the group that we see at this beta 2 position? We see 3 methyl groups. If there's a methyl ethyl propyl here, we might have to do this 3 times, but I'm doing this on purpose. We have the 3 same groups here. So it doesn't matter if we take this one, or this one. But these bonds are full of electrons. This wants electrons. This molecule could undergo what's called an alkyl shift. In this case, it would be a methyl shift, because carbocations want electrons, and these things can move and shuffle around and rearrange, especially if they make something more stable. We would call this 1,2 We could call it an alkyl shift. But the specific group we're using is methyl. So we could call this a 1,2 methyl shift. Alkyl is a general word for the alkyl substituents. Methyl, ethyl, propyl would all be alkyl, but specifically this would be a 1,2 methyl shift. We're just moving it 2 carbons, 1, 2. If we do that, we break this bond and we make a bond here. Newly formed bond would be here, and we would get a tertiary carbocation if we did this. Here we've gone from secondary to tertiary, so we're going to keep this. This would be energetically favorable. And this happens because carbocations are so friggin' reactive. They really don't like being formed at all. And so if we form an unstable carbocation, it will hunt and search for electrons within itself, sometimes even before it finds external electrons from a nucleophile. So this is a keeper, for sure. It's tertiary, it's more stable than where we started from, and if I pull out that slide from moments ago, or our notes from before, I know this is a little bit messy here, but in our notes before, the unexpected product we characterize as being tertiary alcohol. Look at these two things carefully right now and see if you can see the connection. I know it's tricky. I know we're all over the place here, but look at these two things and see if you can see the connection. They're drawn differently for sure. All right. There's more color here. Methyl groups are drawn expanded. Here they're all in stick formation, line bond drawing. So we've made a tertiary carbocation, and does it actually match up with this or not? Well, we'll finish the mechanism to explain this. I'm hoping you see some similarities between these two. If not, we'll make it connected right away. But we now have this tertiary carbocation. It's better than where we came from. And we're simply going to add water to this one. Okay, so this is just the same thing redrawn. These two are the same molecules. If we add water to this position, we'll have this oxonium ion intermediate. And if we just do this loss of an acidic proton, we can explain the formation of this rearranged product. So, this explains the formation of that rearranged product. I know what we just went through might be a little jarring. There's quite a bit of things going on here, but there's a systematic way to go about this, which I've demonstrated to us. There was a problem when I put up the example we were working with right from the beginning. There was an unexpected product that I demonstrated in this first example. In this example right here, I just put it up on the board without any mechanism. So we have this substrate and water. It forms this alcohol, which all of us should have been able to predict, and it forms this unexpected one. If we looked very carefully at it, we could see that the carbon skeleton has rearranged. There's a T-butyl group here, a T-butyl group here. There's no T-butyl group here. There's an ethyl group off to the side, an ethyl group off to the side. Here, there's no ethyl groups. There's 2 isopropyl groups. So seeing this might give you a queasy feeling, but you can just say, okay, well, this just means the carbocation is rearranged. What we did next was we explained the formation of the simple product that it's just practice of SN1 reaction. This comes from a carbocation. And since this comes from a carbocation rearrangement, the process I'm teaching you how to do now is to redraw and re-examine this carbocation, and we're going to examine can we move things around only from beta positions and only one time? We don't do shift, 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 shift. We just do one shift and only from these flanking positions. And if we can find one that works to make something more stable, we'll keep going and keep exploring. What we did, we first examined the beta 1 position. The way we examined the beta 1 position, here's our original carbocation, and all we did here was expand. Just draw these out, see the atoms, see the bonds, and move one. This is called a hydride shift. And if we move it from here to here, the carbocation reemerges at the primary position, and energetically this is uphill. We're going from bad, which is secondary, to worse. Okay, doesn't work, so we just aren't going to explore this further. Kind of makes sense from an energetic perspective. We then turn our attention to the other side of the molecule. The beta 2 position, we had 3 methyl groups. We can move these electrons. This is called a alkyl shift or a methyl shift. The carbon skeleton rearranges, the connectivity of atoms rearranges, and the carbocation rearranges to a more stable tertiary position. We should definitely keep this now that we know it's possible. And if we keep this carbocation and redraw it, it's tertiary, we should be looking back and reflecting back, and we'll see the connection to the tertiary product we formed in the initial step. So this is going to take some practice. I'll put a few more examples here. I'll answer whatever questions hiding here just in a moment. But another thing we can do when we first start out with this problem, just in the very basic sense of it all, first product should be easy. The connection should be easy with our in-depth knowledge of substitution chemistry now. We should see and think already, well, this is SN1. This comes from secondary carbocation. This is from an SN1 reaction. It's rearranged, and it's a tertiary carbocation. So even if we think about this carbocation, you can even look at it a little bit, where this little red dot is, or where this pin is pointed where the carbocation would be. And the alcohol ends up over on this side. So you might even think, I think we should always explore both. It's good practice. But even just looking at this, your mind might be biased right away. Oh, this is a more substituted side, so if I move one of these, you should be able to make something better here. You can start foreshadowing and leading your mind that particular direction. But by taking this process of taking a carbocation, labeling it alpha, labeling all unique positions beta, call them beta 1, beta 2, whatever you want to call them. Explore them systematically. First, look at this one, good or bad. Second, look at this one, good or bad. This process, right, is the process that will always help you explain these. This is going to be on our third exam. It's not the most important thing we're doing, but for those students striving to do their very, very best work at the very, very highest possible grade in this course, you have to work towards an understanding of this. This is very challenging material, I get it. So everyone should work towards some understanding of this, but if you're struggling with more basic things of SN2, SN1, your attention has to be there first, okay? Yeah, so there's